Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is Nurul Asmira binti Zalani. Matrix number Ka18044. So today I would like to present about the production of the 30,000 metric ton per annum of 1,2-propandiol by the Aspen Plus. Okay, so the introductions. The objective of this project is to stimulate the process for the production of the 1,2-propandiol with the capacity of 30,000 metric ton per year, together with the priority of the 99.9 weight percent. The reaction of equation that involve is the glycerol added with the hydrogen, producing the 1,2-propandiol and water, and also the glycerol added with the hydrogen, producing the ethylene glycol and methanol. The 1,2-propandiol is the main product. Meanwhile, the ethylene glycol and also the methanol is the valuable side product. And then, okay, so for the first question, determine the thermodynamic model and justify the selections. Okay, so we are choosing the Unicrack as the thermodynamic models according to the Bob Sears recommendations. Besides, the Unicrack is chosen for the liquid phase activity. According to the Bob Sears recommendations, we identify the presence of the hydrocarbon and also the polar compound of the component. So we conclude that the chosen of the Unicrack as our thermodynamic models. However, when the binary parameter is not available, then we use the Unifact. Hence, these two thermodynamic models is chosen due to the presence of the hydrocarbons and the polar compound. In addition, in order to calculate the liquid density using the API correlations, the dissociation column T104 for the separations of the propylene glycol and also the ethylene glycol, thus the Peng-Robinson is used. For the next question is for the question 2, perform the binary analysis for the component involved in all thermal separation unit. So for the first diagram is the binary analysis of the TXY diagram for the water and also the propylene glycol. Okay, the two components will be separated at the dissociation column T102, which is for the separation of the water and also the propylene glycol. Thus, since there's no occurrence of the H2O of the azeotrope, thus the common distillation column will be used. And for the second diagram is for the TSY diagram of the methanol and also water. The third diagram is the binary analysis, the SY diagram for the ethylene glycol and also glycerol. Meanwhile, the fourth diagram is the TSY diagram for the propylene glycol and ethylene glycol. So based on the figure that have shown before, we observe that there is no azeotrope occur. Thus, a distillation column can be carried out to separate this mixture. And we are using the common distillation column for the T101, T102, T103, and also T104 as in figure below. And then for the question 3, we are required to draw the PFT. Okay, so for this PFT, this PFT is established to produce the 30,000 metric ton per annum of the 1,2-propandiol with the purity of the 99.9%. We have the mixture whereby we will mix the raw materials and then heat exchanger either to heat up or cooling down. For example, the E101, it will heat up the component to enter the reactor, and then at the reactor we are occurring two type of reaction, which is it will produce the propylene glycol, the water, ethylene glycol, and also the methanol. And then we have another exchanger whereby it to cool down before it enter the flash. Okay, in the flash column, the top product will be hydrogen, whereby it will recycle back into the mixture. And then the bottom product, it will have the methanol, water, propylene glycol, ethylene glycol, and also the glycerol. After that, it will continue with the further purifications of the component until we get the desired product, the desired purity, the desired product, which is the propylene glycol, the desired purity, and also the product capacity. Okay, for the question 4, we would like to determine the feed material flow rate to achieve the desired plant capacity and the product specification. So there is a few steps, which is for the first step, the plant is assumed to be operated for the 333 days in a year with the operating hours of the 8,000. And then we gathered all the information from the journal, whereby the glycerol having the 75 weight percent and the water having the 25 weight percent. We also assuming the basis of the 100 kilogram of the glycerol feed. So the glycerol mass will be 75. Meanwhile, the mass the water mass will be 25. After that, we change the mass into the mole by multiply with the molar mass, and then we got the mole for the glycerol 0.8152 and also the moles for the water 1.389. After that, we will calculate the mole percent of the glycerol 37%, and the mole percent of the water is 63%. We then continue with the glycerol, calculating the flow rate of the mole flow rate of the glycerol. We got the 100. Meanwhile, for the water, we got the 170.27. Other than that, there is a ratio between the glycerol and also the hydrogen, which is the 1 glycerol is equal to 5 hydrogen. Thus, we are calculating the values. The mole flow rate of the hydrogen is 500 kmol per hour. We then substitute all the values into the feed stream, and then we run the simulations. However, the actual production was not at the desired capacity. Thus, we are actually doing the scaling down calculations, whereby it will be shown in details in the question number 7. We got the 66.284 for the glycerol, mole flow rate for the glycerol, water 112.753, and also for the hydrogen is 331.1. Thus, from this molar flow rate, we will get the desired production, which is 30,000 metric ton per annum. And then for the question 5, we are going to describe in details the step for the model reactor. Okay, so we are using the RCSTR, and the temperature is 205, and the pressure is 20 bar. After that, the valid phase is selected to be the vapor liquid, and also the value of the 5 hours is the first gas for the residence time, and then we run the process. After that, we are adding the reactions, whereby we choose the type of the power law. We are substituting the stoichiometry and also the kinetic that is provided in the question given. So the values will be substituted into the span. After that, there is one thing here, whereby the rate for the reaction to 444, the values for the A 444 to the power of 6 will be modified into the 4.44 to the power of -8 in order to achieve the desired productions of the desired product. Thus, we substitute the values and also the stoichiometry. The glycerol and hydrogen coefficient is -1 since it was reactant, and then producing the propylene glycol and also the water. For the reaction 2, we are adding the glycerol and also the hydrogen, and then we will produce the ethylene glycol and also the methanol. After that, adding the kinetic, substituting the values that provided in the questions, and then we run the reactions. We select the R1, and then the initial run is done, and then we continue with the design specification in order for us to identify the desired the actual values of the resident time. The targeted conversion is 87.7 for the glycerol, and then we are varying the variable will be the resident time. Thus, from the stream result, we create the resident time is 5.40413 to the power of exponent to the power of 7. We substitute back the values into the specifications, and then we run the simulation. We observe from the stream results, we will get the conversions is 87.7, which means we get the desired conversions. For the question 6, describe in details for the verification shortcut distillation column, whereby we use the DSTWU for this part. Okay. In this example, that the product recovery to achieve the highest level of the purity of the main product has been proven successful based on the outlet stream of the distillation column with the specification used, whereby if you can see from the outlet stream of the propylene glycol, you get the 44.9023. Meanwhile, for the water, we will get 157.528. We will use the same method and the same approach for the different distillation column, whereby we apply to the distillation column 1, 2, 3, and also 4. Okay, optimization to determine the optimum number of stages if the stage reflux ratio and other necessary column operation. So assume the reflux ratio. Okay, first we are assuming the reflux ratio is 0.2, and then the result that will be came out is error, but still we can use the values, because the DSTWU is a corrective action and it will calculate the actual ratio. And then all of the results such as the optimum number of stages, refract ratio, to fit ratio, and others will be substituted into the refract later. Okay, so this is how we do the simulations, whereby we put the 0.2 at the refract ratio, we run the simulations, and then we will get the actual values of the refract ratio and others values. And then all of these values will be substituted into the refract soon. Okay, this is how we substitute into the refract. We do for the refract T101, T102, T103, and also T104, whereby it follows the DSTWU results that we get before this. Okay, so based on the design spec input at the T104, the purity of the outlet stream of the main product was achieved, which is the 0.999. And then to stimulate the overall process without recycling to achieve the desired purity and the capacity. So this is the PFT for the overall process without the recycling, whereby we don't recycle the hydrogen. So the process will be stimulated with the property method of the unified to maintain the appropriate production rate of the reactor. However, to achieve the appropriate separation, the T104, T101, T103, T103, T102, T103, we will use the uniquack. Meanwhile, for the T104, we will use the Pangrok. And then for the V101, we will use the unified model. Okay, so all of these values and also condition will be getting from the journal provided. um, and then the main vision is to get the product specification, which is a 30,000 metric ton per annum of the 1,2 diol with a purity of 99.99 weight percent of the purity. And then even after we run the simulation, we didn't get the actual production capacity, whereby we we will get we will get okay, we will get the actual production capacity, because at first we are assuming as a 100 kmol per hour, but after we do the details, the scale down details calculations, we will get the different flow rate at the inlet. Thus, it will result us in getting the optimum values of the capacity, the production capacity. For example, this 45402.1, when we are assuming the 100 kmol per hour basis. After that, when we are changing into the actual values, we will achieve the desired capacity. This is how we do the scaling down factor, whereby the actual desired capacity divided with the values that we got, and then we multiply with the off flow rate, so we will get the new flow rate. And then after substitute the new flow rate, we will get the desired capacity, which is around the 30,000 metric ton per annum. However, we still didn't get the purity, the required purity that we want. After that, we use the design spec at the T104 in order for us to achieve the desired purity. After doing the design spec, whereby we put the target values of the desired purity is 0.999, and then following the next for the simulations part, and then the production rate is achieved, and also the final purity of the production rate is also achieved. And then for this question 8, we are going to recycling the we would like to add the recycling loop, whereby we will recycle the hydrogen back into the mixer in order for us to observe in order for us to do the further observations. Okay, so when we are adding the splitter, the split fraction will be 0.9, and also we will inserting the initial values for the hydrogen because we add the mixer just now. And then we'll observe that after getting the recycle, we meet the production rate of the productions required, which is 30,000 metric ton per annum, but we don't meet the desired purity, which is we want 99.9 weight percent. Thus, we have to propose with the design spec. We do the design spec again with the recycle, and then we will achieve the desired purity and also the desired production rate. Okay, based on the raw material consumption, we can see that when we recycle, there are only only 86.005 kmol per hour of hydrogen needs to be fed in the makeup stream from the outside, which is saving the raw material around 244.902 kmol per hour of the hydrogen subsequently. However, when you observe into the energy consumption before and after recycle, we can observe that the energy requirement is increased if we add the recycle stream. It may be due to the reason of the recycle stream, whereby we add the extra mixer and also the splitter. That's all from me. Thank you.